Good evening, everyone. We can just get started with today's evening session. So, for those of you who are watching on YouTube, welcome to the Cosmic series again. This is our fourth session. We've had over 2 weeks of actually 3 weeks of sessions almost every weekend now. And we're very excited about this collaboration with over 13 clubs, and the response has been very enthusiastic. We've also had some of the most eminent scientists across India coming and delivering amazing lectures over the last few weekends. So today's session, we would like to host it as Nakshatra Sciences, and we are very happy to invite a very special guest today. Just before we get started, if you're new to the platform, Nakshatra Sciences is a project-based learning community. And if you're new, you can join our different community servers on Discord and Telegram. We offer opportunities to students to work under different scientists from institutions across India in several domains like astronomy, environmental sciences, as well as mathematics, programming, etc. So, if you're interested in research projects or just joining a study group or a club, then you're invited. A lot of our activities are completely free and open for all students to join. So now let's talk about our guest for today, and we're very happy to have him because we've covered different topics over the last few weeks, including radio astronomy and X-ray astronomy. But today we will focus on theoretical astrophysics, and I think a lot of you are aspiring theoretical physicists, so it's going to be an exciting talk. So welcome to our platform, Dr. Dishant Pandya. He has finished his bachelor's, gold medal, and master's first class with distinction, as well as MPhil degree from Sardar Patel University. He did his PhD from the Maharaja Sayajirao University of Baroda, Vadodara, in the field of Classical General Relativity, that is a solution of Einstein's field equations, and created a large class describing the compact stars. He is carrying 13 years of teaching experience and 3 years in industry. He has published several research articles and also written a book chapter. Currently, Dr. Dishant researches theoretical astrophysics, applied mathematics, image processing, geometry, and so on. His most recent publication is Models of Compact Stars of Embedding Class 1 for Anisotropic Distribution Satisfying Karmarkar Condition. I think over the next 1 hour or so, all of us will have an opportunity to learn more about his work. So please be free and open to ask him questions during the Q&A session. And finally, welcome, sir. We can get started with today's session. If you feel you want to pause in different parts during the talk or accept questions, you can always do that. And once again, thank you so much for coming here and spending your time.
Thank you so much, Sidhara and Sagar, for welcoming me here and giving me an opportunity to discuss space research in cosmic terms. Thank you very much once again, heartily. And let's start our journey. I hope you might be seeing my screen. Am I audible?
Yes, sir. We can see the screen. We can also see you.
Fine. So let's begin with a research journey into space, knowing the unknowns. So basically, just like you all guys, and many of you are might be, amateur astronomers, and they really like sky gazing, and they're really fond of hearing about stars and planets and comets, etc. Right? So I was in the same boat. Okay, before a few years, when I finished my master's degree, I was keen to do research in the field of space science. So I basically scored higher in physics in order to pursue my career in the field of space science. I was knowing this thing very well, and because I interacted with few of the scientists during my graduation and post-graduation, and I came to know that for if you want to pursue your career in space science or maybe in astrophysics, you need to have a good command over physics as well as mathematics. So let's see that what are the things that you need to see first of all when you want to enter into this field. If you see, there are plenty of categories and research aspects in this field. However, you can just divide this into main three parts. The first is the space where you are studying with black holes or dark matter or gravitational waves, astronomy, astrophysics, and the space physics. Okay, so it's a large class here that you are basically working in the space section. The other category here is planets. So are there any other planets like Earth which is habitable? Okay, and what will be the atmosphere on that planet, and what will be the geology or meteorology of the planet, or maybe the surrounding area. Okay, so these all things come into picture in the planetary sciences. And the third section is life sciences. So if even if you have a good command over biology, you can still become a space scientist, where you will try to find the life on other planet, or maybe you can see that can you grow plants in some other planets, maybe on Mars or some other planets. And similarly, I mean, there are plenty of theories coming out there which are evolved for the section of life. For example, are we, I mean, can we see that, can we see ourselves that we came from asteroids? So something like this strange equations, or I mean questions. Okay, so if you want to solve such mysteries, you can choose your career in this life sciences in the planet and beyond the planet. So these are the categories that you can think about. Now, coming to the key element of our space, that is called stars. Basically, you all are familiar with the Magellanic Cloud. So if you see a large Magellanic Cloud, there might be a new star formation each and every second. If you see, okay, thousands of light year away from our planet, if you see such kind of Magellanic Cloud is already exists, and it gives birth to stars. Okay, so this is the starting point of our star. So basically, it's a process by which dense regions within molecular clouds basically forms the star. Okay. Now coming to the next thing, that is what will be the stellar structure described by the sun. Okay. First of all, why I have taken sun? Because this is the closest star. Okay. This is the closest star to the planet. Okay, so sun is our first star that we see every day in our life, and beyond that you have a very distant star, say nearly 4 light years away, which is the nearest star. Okay, so basically these are all stars, and we are really interested to understand the structure of the star. Okay, so internal structure will lead to the prediction of many factors like luminosity, color, and the fate of the star. For example, here, if you see the cross section of our sun, it consists of many portions. Okay, so there are sunspots, there are penumbra, penumbra and umbra regions. Then also you can see here solar winds, the inner core part of the sun, then solar flares, chromosphere. So each and every region has its own characteristic. Okay, so basically, if you understand the structure of sun and its relation with science, it will be really useful to you when you develop your knowledge in order to contribute to the society, in order to contribute in the field space science. Okay, so there are various scientists who are working very actively in, say, for example, studying solar flares. Okay, and how they occur, and when they will again occur, and etc. etc. Okay, there are n number of possibilities that you can study with this field. Okay, and also there are giant sunspots, okay, which you can study. So let's first of all understand the fundamental mathematics which is involved in the stellar structure. So basically, you can say that you are going to consider spherically symmetric quasi-static model, which assumes the star is in steady state and it is spherically symmetric. Okay, so this is the first thing that usually we are starting with our terminology of spherical symmetry. Okay, so and we also know that when you have a very high gravity at that time, it may happen that the structure may not be exactly symmetric. Okay, but still we are starting to work with spherical symmetry. So it contains basically four basic first order differential equations. So out of those four equations, two represent how matter and pressure vary with radius, and the remaining two, they represent the temperature and luminosity variation with radius. Okay, so when you see the formation of stellar structure equations, you may consider the matter density, that is rho r, temperature, that is Tr, total pressure, that is matter plus radiation, that is Pr, luminosity Lr, and energy generation rate per unit mass, that is epsilon r. In you are considering this in a spherical shell of thickness dr at a distance r from the center of the star. Okay, so if you see, these are the parameters, and if you see it lightly, you might have studied the similar kind of thing in your calculus part when you are studying the finding the volume of a cylindrical shell, something like that. Okay, so you just try to correlate this thing with your fundamental mathematics. Okay, and here star is assumed to be in local thermodynamic equilibrium. So the temperature is same for matter as well as photons. Okay, so this is the thing, and let's see what are the four equations which are basically involved here. The first equation represents hydrostatic equilibrium, that is dp by dr is same as minus gm rho upon r square. What does this mean? It means that the outward force due to pressure gradient within the star is counterbalanced by the inward force due to gravity. Okay, here mr is nothing but the total mass inside the shell at r, at a distance r, that is the radius of the star, and g is the gravitational constant. Okay, that is the first equation that we need to use it. The second equation is the equation of continuity. You might have seen this equation in several places, including fluid mechanics. So here we are working with the mass thing. Okay, so this is called cumulative mass, which is increasing as your radius. I mean, it depends directly proportional to radius. So as your radius increases, your mass increases. Okay, and therefore the mass continuity equation can be represented by dm by dr is equal to 4 pi r square rho. If you integrate this, you will get the total mass from the center of the star to the outer part of the star, that is central to the boundary. Okay, that means integration from 0 to capital R. If you integrate this, then you will get the total mass inside the star. Okay, total mass of the star. The next two equations, considering here, if you have energy which leaves the spherical shell, then how can you calculate that energy? So it has a connection with this equation. This equation is dl by dr is equal to 4 pi r square rho into bracket epsilon minus epsilon nu. Here epsilon nu is luminosity produced in the form of neutrinos. Now neutrinos occur when you have strong interactions with proton and neutron. Okay, so very high energy when it exists, you have such kind of structure available. Okay, so outside the core of the star, where nuclear reactions occur, there is no energy is generated, and hence luminosity is constant outside the star. So this is very important phenomena when you want to study the structure of the star. And finally, the fourth equation called transport equation or energy transport equation. And it differs from various to various situations, but generally, if you go with the standard way, it can be given by this equation, dt upon dr is equal to -1 by k, 1 L upon 4 pi r square, where you are using thermal conductivity into picture. Okay, so when I studied this thing, at that time, I just moved forward and I thought that not only the sun, but there are other stars which are having tremendous energy and mass. Okay. And when I started my learning in that point of view, I just came to this thing that is called neutron stars. Basically, neutron stars are really interesting objects to study, and the reason behind this are n number. So, for example, the first thing here is when you are considering a star whose mass is almost 4 to 8 times higher than the sun, okay, and it explodes in supernova, what is called as supernova. When it explodes, at that time, its outer layer, it totally blew off and only dense core remains there. And this dense core has very lower radius. If you even compare, it's not higher than the Ahmedabad city as well. Approximately 8 to 10 kilometers in size of the radius, this dense core will be there. And since it has very less size, it has tremendous amount of gravity. And this gravity presses the material so tightly that you have proton and electron, they are merged to get neutrons. So ultimately, if you see such object, it has purely neutrons available. And that's the reason these objects are called neutron stars. Okay, so this is quite fascinating, right? And hence, you have the object which is of very less size, but it is of having very tremendous energy. You see here, it may have mass inside this 20 kilometer diameter, which is tremendous. And even if you consider a single teaspoonful of the material of that neutron star, it would weigh 1 billion tons. So obviously, I have made here one statement. So assuming you somehow manage to snag a sample without being captured by the body's strong gravitational pull, otherwise you can not measure that thing. So ultimately, the idea behind this is it has a very higher density. On an average, if you see, gravity on a neutron star is 2 billion times stronger than our gravity on Earth. So if you see, if you are having the same body which is on Earth, now if you are on neutron star, your own self, your body's weight will be in billions kgs. So you see, okay, where we have. So in fact, it's strong enough to significantly bend radiation from the star. This process is known as gravitational lensing, okay? And this allows astronomers to see some of the backside of the star. So this is an added advantage of seeing a very high gravity. Next is the power from the supernova that burst, it gives the star an extremely quick rotation and causing this to spin several times in a second. So neutron stars can spin as fast as 43,000 times per minute, and gradually it may slow down, but the initial speed is very high. You can say tremendous speed, 43,000 times per minute. Now, stars are, which are more than 10 times as massive as the sun, they transfer material in the form of stellar wind. And the material flows along the magnetic poles of the neutron star. It creates an X-ray pulsation. Whenever there is some heat, okay, it produces X-ray. And that is the reason that these are given a name called pulsars. They are pulsating something. And if you see even in the recent history, you see here, we already have observed more than 1,800 pulsars, okay, through our radio detection and radio telescopes. and another 70 gamma rays burst as well. Okay, so gamma rays, we already found this. Now, some pulsars even have planets orbiting them, just like our planet. Okay, so this is again an interesting story behind the neutron star, why I have chosen this subject in my research study. Okay, now there are some, few types of neutron stars that you can think of. First of all, there are some neutron stars, they basically have some jets of material streaming out of them. Okay, so basically they are ejecting some material, and you are just noticing the thing which flashes like a bulb of lighthouse. Okay, and therefore these pulsars are, having such kind of characteristic. Normal pulsars spin between zero point 0.1 and 60 times per second, while millisecond pulsars can result as much as 700 times per second. See, so millisecond pulsars are really stronger objects. Okay, they basically have that kind of tendency to have a pulsation of 700 times per second. Okay, now coming to this X-ray pulsars, basically they are capturing the more massive companion from the around things. Okay, so basically it interacts with the magnetic field to produce high powered beams, and since it consumes the thing nearby, we are using the word accretion powered pulsars. Basically it can be seen in the radio, optical, X-ray or gamma ray spectrum, and the main power source here, it comes from the material from their companion in the sense that you are familiar with binary system of stars. Okay, so if some other smaller star is there near to the neutron star, it basically consumes the stuff from the other star. Okay, the higher powered star basically consumes the stuff nearby, and that's the reason that accretion powered pulsars will be formed. Another option here is spin powered pulsars. They are basically driven by the star's rotation as high energy electrons interact with the pulsar's magnetic field above their poles. So this is another type of pulsars that we are seeing. Now, as material within a pulsar accelerates within the magnetosphere of a pulsar, we find here gamma ray emission, and the transfer of this energy in these gamma ray pulsars slows the spin of the star. So gamma ray pulsars are also really interesting story. Okay, you can see you started with the observation with the fast rotation, then you in fact realize that this rotation will gradually slowing down. Also you are facing here the thing that you might see the gamma ray emissions. Okay, so you might witness the gamma ray emissions here, and the flickering of pulsars is so predictable that researchers are considering using them for space flight navigation. Now see the importance of neutron stars. Have you ever thought of this thing, that we can in fact use this as our navigation thing, because the flickering of pulsars, the emission at each and every, the frequency of this emission is so symmetric that you can in fact rely upon it. And not only this, but some of these millisecond pulsars are extremely regular, like clock-like regular. So Keith Gantreau of NASA's Goddard Space Flight Center, he basically mentioned this thing, and also he told that we use these pulsars the same way we use the atomic clocks in a GPS navigation system. So how these neutron stars are interesting in research. Okay, it has tremendous energy, it has tremendous potential for our research as well. And you see, this was really a heart-touching point for me, that yes, neutron stars are really useful, and we definitely need to study these objects very well. And you see here, the average neutron star contains a powerful magnetic field. Okay, let's see some of the interesting, more things here in neutron stars. If you see Earth's magnetic field, it's around 1 Gauss, and Sun's is around few hundred Gauss, right? But if you come to any neutron star, you have trillion Gauss magnetic fields. Now see, the thing here It has trillions of gauss magnetic fields, and this is, you can say, really an awesome thing that you need to understand very well. Now, coming to the other part, that is called magnetars. Basically, magnetars are the neutron stars which are having the strongest magnetic field. Okay, they are having the strongest magnetic field in the universe. Okay, so it has even higher magnetic field, 1,000 times higher, stronger than the average neutron star. So these are called magnetars. Basically, they are not only neutron stars or X-ray pulsars, but they are having strong magnetic field and hence the name magnetars. So these are the reasons that why I keenly interested in doing research on the ground of mathematics in the theoretical astrophysics. So why theoretical astrophysics? Because I could now use my knowledge of mathematics, the mathematical modeling of natural phenomena in astronomy and astrophysics, and any student can calculate model outcomes by simulating or solving the relevant physical laws which are engaged in this area. So this is really, you can say, a thing which has, you can say, some insight when you want to build your career in the space science field. You need to have a good and, I mean, clarity of thoughts here, that in which field basically I need to study. Okay, and based upon that, you should basically start your career from graduation itself. Okay, so that when you finish your post graduation, you will be in a position to pick the right topic. Now, there are various criterion for getting the physically viable model to describe the complex stars. I will show you this in detail, but before we dwell into that thing, let me show you these conditions. Okay, in one of my research papers, I mentioned these conditions. These are the conditions which are really important when I am creating mathematically, or you can say physically viable solutions. Okay, and to represent the large class of compact stars. Compact stars are basically, you can say in simple language, it's neutron star. The class of neutron stars which you can cover here on the basis of mathematical modeling. So on the left hand side, you see here, there are some conditions which are required. The first is regularity conditions. In regularity conditions, you have three sub conditions. The first one is you need to consider a metric potential e raised to lambda and e raised to nu in such a way that they are positive in the whole interior to exterior region. I mean the whole star. Okay, 0 to capital R. And then you have this rho r, PR, and P perp. That is, now what are these quantities? I will just let you know after a few minutes. Similarly, the other conditions, PR should be 0 at the boundary. Then causality condition, that is the sound speed. It is related with sound speed, so it should be in between 0 to 1. Then energy conditions, strong energy condition, weak energy condition. And then on the right hand side, you have some monotone decreased nature of physical parameters. Next thing is pressure anisotropy, mass radius relation, redshift, and stability conditions given by various scientists. So if one and all, if you consider a very good model, then it should pass from all these conditions. Okay, so even if one condition is not matching, your model is not physically viable. Okay, you can say that your model is not of that much usefulness. Okay, so you need to reconsider your model and modify in such a way that all these conditions should be satisfied. This is our main target, right? And these are some of the outcomes that I wanted to show you. The left hand side is the variation of density, and I mean all these things I have considered the parameter MEV per Fermi cube. And you can also see here in caption figure 1 for U 18, 20, 30. So this is one of those pulsars, okay, which we have considered, okay, for our study. And the radius as well as some of the relevant parameters we have calculated, and we modeled here star, I mean the physical properties of the star in 3D. Similarly, on the right hand side, you have radial pressure, and the left hand side is transverse pressure and dpr by d rho. Okay, now coming to this thing, let me just show you one thing. The first thing here is, when you are discussing abnormal star like neutron star, you need to consider the asymmetry, that is non-symmetric nature as well. Okay, so usually we are considering a spherical symmetry, but what we need to think here is, when you are considering such high pressured a very strong star, I mean a star with strong gravity, at that time it may happen that you lose your spherical symmetry, and at the same time you might be dealing with radial pressure and transverse pressure. These are two perpendicular components to each other, which basically leads to anisotropy. Anisotropy means there is no uniformity in the star's geometry. Okay, so this is really interesting, that you now want to model a star which is realistic. The star which is realistic, because we already have observed neutron stars, and they are having tremendous amount of energy and gravity, and that's the reason we can immediately think of that there must be some non-symmetric nature. There must be some radial and transverse pressures which are different from each other, and that's the reason that I'm showing here those components. Okay, coming back to these conditions, now you see here regularity condition, the second part of regularity condition is nothing but rho r is non-negative, that is density, then radial pressure, it should be non-negative, and transverse pressure. So radial and transverse pressure are the components which basically represents anisotropy. Okay, so anisotropy is nothing but here S, capital S. You see the first line, pressure anisotropy. So this S, that is the anisotropy, is nothing but the difference between radial pressure and transverse pressure. So you can say, if you are having that difference which is different from zero, you can say that you are having anisotropy. And if the difference is zero, you can say that you are dealing with isotropic case, right? So here I considered all of these parameters, like left hand side you see anisotropy, and right hand side is dp per by d rho. Similarly, pr by rho, dpr by d rho. These are all mathematical components. I calculated it and tried to check whether these all components are satisfied in the given range or not. Okay, and these are, strong energy condition on left hand side, adiabatic index on the right hand side, and left hand side is gravitational redshift, which should be a decreasing function, and right hand side is variation of mass with some range. Okay, I have found even the range, which is 0 to 3.059. So here you can say mass radius relationship. These are famously known as MR plots. Okay, mass radius plots. So basically, this is very important thing. The reason behind this is, if you consider a large class of pulsars, then how much maximum mass can be accommodated in my model, that can be seen here from this figure. Okay, so maximum mass which can be accommodated here is 3.059, and maximum radius which can be obtained or attained in my model is 9.571. So maximum mass and maximum radius can be accommodated within the given range, so that all these physical requirements are easily satisfied. This is the main motive behind this research. Okay, so how can you say that you have made a successful contribution in this field? If you see that all these conditions are satisfied from top to bottom. Okay, so you see here the signs here. So in some of the factors you are seeing the range like 0 to 1 here in part B, and some of the conditions should be, they should be non-negative, or maybe it should be less than 0 and something like that. So all these conditions must satisfy within the stipulated range. For example, mass radius relation. Okay, it should be less than or equal to 4/9 always, according to Bagdal. So maximum allowable mass radius relation should be there. So if you are considering a model, if you are creating a model which does not satisfy this thing, then we failed. Basically, we need to recreate the model in such a way that all these conditions should be satisfied, right? And this is the thing that I wanted to show you. Now you see here some of the things that we came across while working on this problem. On left hand side, you see the stars, and which are having, which are having these properties. So the stars radius, then I listed down the geometric parameter L, and then P pup, then all other parameters on left hand side. Now the second column, basically it's a first pulsar that we considered, that is PSR J1903 plus 327. Similarly, there are some other pulsars. Okay. Now, why we considered these pulsars? Because in Gangopadhyay et al., they have worked out nicely on some of the pulsars, and this was picked out from those pulsars. These pulsars have observed radius and mass as well, right? So basically, our observatories have detected these pulsars, and basically now they are knowing that this should be the radius of this pulsar. That is the reason that when we created our own mathematical model, we basically implemented those things here on the realistic problems, realistic stars. So these are the stars. When we employed our model to these stars, then we could drag out that these are the values. You say here, our alpha, that was a parameter which we considered, it basically gives a very nice relation here in each of the cases. Okay. So in fact, central redshift, surface redshift, final bound on alpha, and similarly gamma should be greater than 4/3, and all these parameters, which gives me a very nice connection for my alpha. And obviously, I could obtain the range of alpha in such a way that all these conditions on the left hand side, they hold good for all the considered pulsars, right? And this was the thing that basically we worked out. Now, coming to the next thing, just a minute. Okay. Now coming to the next thing, if I really wanted to see such kind of structures which I depicted before few minutes, I need to have some fundamental concepts. And that's the reason that we are studying general theory of relativity. So basically we consider Riemannian spacetime here, Riemannian metric. Along with that, we need to solve Einstein's field equation. Because if we don't solve Einstein's field equation, we cannot create those parameters which was listed earlier. Okay. And so we need to understand Einstein's field equation, and which basically gives the relation between matter and energy, along with some tensorial analysis. And since you might be a graduate student, some of you might not be knowing that much tensor analysis in detail. And that's the reason that I'm not going into much detail about tensor analysis at present, but I'm just showing you the expressions, that these are the expressions which will be involved while solving Einstein's field equation given by 2. Okay. So these tensor analysis, along with the Christoffel symbols of first kind and second kind, I need to go further to use these relations. And whatever the differential equations that are created there, I will try to solve it out. Okay. These are some of the properties which are already we discussed and listed out here as a compact stars. We start with perfect fluid where there is no shear stress or anisotropic pressure and no viscosity. Okay. But when you want to consider anisotropy, just I told you, radial pressure should be different from transverse or tangential pressure. So the first time, this was the thing which was posed by Ruderman, then Canuto and Bowers and Lian. Okay, they reported this thing that in high density regime, there must be anisotropy. And hence, it would be more realistic to study anisotropic fluid distribution rather than studying perfect fluid. Okay. Later on, when Maharaja and Martens in 1989, they suggested that now new electromagnetic energy momentum tensor for anisotropic fluid distributions, this can be given by the equation number 8, okay, where Tij is nothing but rho plus P Ui Uj minus P Gij plus pi Ij. Rho is here proper density, P is the isotropic pressure, and U is the 4 velocity field of the fluid. So when you consider 4-dimensional structure, you are going to use this 4 velocity of the fluid. And then they carried out their computations further, to create equation number 9, then relations 10. And after solving this, they found the relationship between radial pressure and transverse pressure, which is divided by root 3, gives you an anisotropy, magnitude of anisotropy. Okay. And obviously, when your radial pressure is same as your transverse pressure, then your anisotropy is 0. Okay. So whenever you have some models which already exist for isotropic case, and when you have natural extension of anisotropy, at that time you will try to go with anisotropic, construct your model, and then when you switch to the isotropic case, I mean when you consider PR equal to P per, it should directly match with your isotropic case. So if it is not there, then obviously we have made some mistake. Okay, so this is, you can say, a cross check for your calculation. So recently, all the scientists which are, I mean, they are already working in an isotropic field. What they are doing is basically they are already doing the connection with already established models. Okay, so the model is there, and then they are trying to get extension of that model. Ultimately, what they are doing is they are basically trying to match and correlate the model with the earlier one. So if there is one-to-one mapping, you can say that all is well, your model is good, and you have made a good extension to the model which is already existed. Okay, now for this workout, I need to consider few spacetimes. The first spacetime is spheroidal spacetime metric. Okay, the students who are having and the theory of relativity subject in their graduation or maybe in post graduation, they might see some kind of structure. Or for the students who are studying differential geometry and Riemannian geometry, they might see a similar kind of thing in their curriculum. Okay, so we start with any particular metric, and along with some conditions, you have established model for that particular metric. Earlier metric was spheroidal metric. This metric was posed by Tikaker and Thomas in around 1999. And this model was also a very good model to study certain stellar structures. This is called pseudospheroidal spacetime metric. The third one is called paraboloidal spacetime metric. And you see here, out of these all models, okay, the paraboloidal was, I mean, in a simpler way, simpler format. Okay, so what I did is I started with this equation, and then along with the set of these Einstein's field equations, if I convert it into the form given by Maharaja and Martins, they are given by 21, 22, and 23 equation numbers. Okay, so basically I need to solve these equations and then let us see if we can solve these equations. You can go further to create the model. Okay, so what I did here is the alternating form of 21, 2, 3 is given by 4, 24, 5, 6, and this M, if you remember this, I already talked about this thing earlier. Okay, so in the initial slides of my present, that when we consider an integration from the center of the star to the exterior of the star, or the radius of the star, the surface of the star, you can say, you can get the maximum mass which is a part of the star. Okay, so the total mass can be obtained with this integral. And now this was the problem which I found very interesting. The problem is in 1989, Finch and Ski, these two mathematicians, they started studying static spherically symmetric anisotropic distribution of matter with this consideration. Now here, what was the new thing that I made? In equation number 32, if you see, if you put n is equal to 1, that was the case posed by Finch and Ski in 1989. Okay, so we started with the generalized thing in the sense that let us see, if we consider the power n, then what will be the bounds or possibilities for the fruitful model? Because you can say around 1990, Delgatti and Lake, they started on studying all these solutions around. They considered check the fruitfulness of the existing models, and then they found that hardly 10 models which basically pass from all these required conditions. Okay, and One of those models was given by Finch, and that is the reason I started with Finch model. Okay, and with power n. Now let us see. The interesting part here is when I started working upon the different expressions which are involved in creating mathematical models, we could see here radial pressure, then e raised to nu, and anisotropic, but anisotropic has really a lengthy expression. So I have not mentioned here all these expressions. And once I found those parameters, there must be a matching with Schwarzschild exterior matrix. Okay, because we are discussing the in should match with the exterior part, and there must be a smooth matching. Okay, so when I match these two things, I could find the value of this capital R, that is given by equation number 40, and capital C. Okay, because constant involved in that integral part. See here, very complex integrals and expressions are. And then I started now employing this thing into this model by verifying that all these conditions should be satisfied. Okay, so I started with gradually one by one condition. Say for example, if you try to understand equation number 42, what does it tell? When PR and P should be non-negative, then I must have the upper bound on P naught. Okay, the P naught is nothing but a central pressure component. So it must be less than or equal to this quantity. ये quantity कहाँ से आई? Because I need to employ these relations. PR and P should be non-negative. So when I employ these relations in my assumption, I will have this bound. Otherwise, for negativity satisfying. Okay, that is the strong energy condition. It should also be satisfied, and for that, P naught has got a lower bound. Okay, so the first, that is equation number 42, was the upper bound. Then equation 43 gave me lower bound. Now you see the nice thing here is now my P naught has got a very strongest bounds. So one by one, when I started working upon all these conditions with all tremendously large expressions, and ultimately, when I just found common interval between all these inequalities, I narrowed down my thing, and ultimately I came to the thing that the upper bound, that is n, should be less than or equal to 4 upon root 3. Okay, and I also found the region of here. I do the graph of P naught and n, where I common. So here the colored region will only give you a fruitful solution. So even if you go either of the side outside of the region, you will get highly. So this was a very good outcome which has been carried out in the first research. And here these are of various geometrical parameters which has been carried out through our mathematical model and the computation. Okay, so left hand side is the list of all the stars which we considered. Okay, the exhaustive list of the star, and on the right hand side we considered these properties on our mathematical model, on the basis of our mathematical model. Now you can clearly match this thing with the existing statistics of these stars, original stars. Okay? So those are observational data, and these are computational data. Okay, these are the data which we have computed on the basis of mathematical model, and those are the highlighted one. You see here the highlighted, the first line in each and every section. Basically, through our computation, we could calculate the exact match of the stars which were really observed. For example, the first star 4U18 2030. Okay, the mass is 1.58. So through our model as well, we could obtain the same radius 9.1 and 1.58. On the basis of that, we could directly predict that this will be the central density of this star, this will be the surface density of the star, and similarly mass radius relationship you can see here 0.2561, and dpr by d rho, which should be having some property at r equal to 0. So you can see here these all things we could work out on the basis of this mathematical model, and these are the theoretical graphical representations of density, then radial and transverse pressures, and variation and anisotropy, then dpr by d rho, dp by d rho, this should be less than 1. Okay, so in between 0 to 1, in fact. And similarly, rho minus pr minus 2p perp, then the graph of pr versus rho. Okay, and similarly, now once we considered that equation, that is the spheroidal one, now we paraboloidal one, and now we started working upon pseudo-spheroidal spacetime. So I'm not going into the much detail of this thing, but based upon these whole computations with different level and strategy, we could here also obtain a very interesting region based upon the parameters involved in this metric, and around almost the same stars which we could obtain by this another geometry as well. Okay, so these are the things which we could obtain. So with this, I conclude my talk, and I hope you must have enjoyed and might got a good idea about how to start the research in your career. So thanks a lot. Any suggestions, any comments, questions?
So am I
Yes.
audible?
Yes, yes.
Thank you very much, Dishant sir, for that wonderful talk. It was very nice.
My
So
pleasure.
yeah, so now I think we're open to audience, and audience, if you have any doubts or questions regarding the talk, please unmute or put your questions in the chat box.
Okay. One question from Dilip Kumar. What are the topic for doing research in future after MSc? MSc Physics or MSc Mathematics? Okay, MSc Physics. Okay, if you are really interested in astrophysics, then what you can do is you can have a good grasp over numerical methods and try to grab the field called numerical relativity. Okay, so once you understand, from the groundwork of general theory of relativity, try to think over the field which is related to numerical relativity. Even if you want to go into the NASA, they people are really seeking for such kind of expertise. So numerical relativity is really an emerging field, and you should go for that. Another option is just like many scientists, they are working in gravitational waves. So that is another option that you start working upon finding the work which is related to gravitational waves or maybe dark matter and dark energy. So these are some of the fields that you can think of. Yes. Any more questions?
Sir, I have one question.
Yes.
So we know that gravitational waves are produced only for very heavy masses, and what are the general criteria of this production of gravitational waves? Like, what should be there for gravitational waves to produce?
Okay. Actually, it's a very good question, and it covers vast knowledge. But let me tell you briefly that when you gravitational waves can be produced mainly on the ground of two things. First thing is it must be a collision between two black holes, or maybe a collision between black hole and a neutron star. Okay, so obviously black hole is the giant, terrific object, which basically it may have consumption of neutron stars as well. So in such phenomena, what happens basically, the energy which is been released at that time of collision, which can be understood on the basis of gravitational waves. Okay, so you are finding that some of the energy that can be released in form of waves, okay, and which are called gravitational waves.
Okay, and I have one more question. So
Yes.
what will be in the interior of these neutron stars? Like, how will matter be? Will it be neutrons, or will neutrons also decompose to quarks?
Okay.
So
Yeah.
how that could be?
Yeah, exactly. That's the reason that sometimes even scientists, they are referring to the words called strange stars. So your question is basically a mystery for many of the scientists, we cannot exactly say for each and every star, but for particular star, I mean, if you want to encompass this in general way, then some of the stars, they really are made of diamonds like that. Okay. And some of the stars might have a quark matter, as you said. Some of the stars are having some other particles. And this is really, you can say, a mystery for all these things. And that is the reason that we could, I mean, we have created those models. Okay. So once you understand that you have that kind of greater density, then what will be the inner content of that star? So it depends highly depends upon those energy density, I mean, densities and radial pressures and transverse pressures and all those things. So you can in fact predict those things.
Okay. And I got many questions from other sources. So those are like, so when we consider birth of a star, like what is the, there is something called as Jeans mass. Like if the mass is greater than that, it's Jeans mass. Like, so we know interstellar gas mediums which are very, very massive, but still why they're not becoming stars.
Okay. Now, in fact, for the creation of stars, there are several components that come into picture. The first thing is, while the creation of stars, it may happen that two nearby bodies, they started, I mean, formation of the stars by themselves. And if the one body, which becomes stronger and stronger, it may happen that sometimes it drags out the stuff which is already existed in the nearby object, which is about to become a star. But basically, with this reason, it could not get that much heating, or maybe you can say the process of diffusion, where it becomes actually a star. Okay, so that is the reason that sometimes it may happen that that particular object may not become a star, but the nearby object become, I mean, brighter star.
Thank you, sir. And one more question is Hawking radiation really a quantum phenomena, or is there some other astrophysical process going on?
Okay, I cannot comment on this thing because, I mean, my area is a bit different from Hawking radiation.
Okay. And one more question is, in the interior of stars, hydrogens basically combine to form helium.
Yes.
So though hydrogen is, I mean, the protons are positive, and when they are coming together, and the energies, I mean, the repulsive force is inversely proportional to R, the distance between them. And when they come very close, it has to go to infinity, but still they are able to fuse. How is that possible?
Okay, actually, this is something called, I mean, we are using the word singularity sometimes. Okay, when the whole matter gets exhausted, when the whole hydrogen converted into helium, at that time the process basically starts shrinking upon. And that's the reason that sometimes you are seeing that thing called supernova. Okay, so when that shrinkage is that much, I mean, powerful, then you are having that supernova first of all, and then the formation of neutron star is happening. So this is the reason that that phenomena occurs.
And continuing with that neutron star question, there is one thing. So mass, if the core mass is greater than 1.4 solar masses, Chandrasekhar limit, then it becomes a neutron star. So what is the mass limit for neutron star? Like when will neutron star become a black hole?
Okay, actually, this is the minimum you can say limit. But when neutron star is basically collapsing, it's see, supernova is the first thing. Then it starts formation of, I mean, neutron star. But even after formation of neutron star, if still gravity becomes so high that it again shrink the object into again and again in the same way, so that ultimately what happens that, I mean, there is no space, and the stuff is, I mean, got into that much depth, so that we have that black hole occurs. Now, for getting that black hole, we must have, I mean, tentatively the mass should be more than, you can say, around 2.4 or 2.5, because you see here the range is nearly 1.4 to 2, or maybe 2.34. That's fine. But even if you have the solar mass beyond that 2.5 or 2.6, you might fall into the black hole.
Okay. And here we have one question. Does any of the models of space explain how the universe will end?
Okay, that is called big crunch. Okay, yeah, I mean there are cosmological models which basically makes you understand this phenomena, but still, since this thing doesn't exist at present, you cannot say that those things are 110% correct. Okay, so yes, of course the models exist, but still, I mean further investigation should be there in order to support those theories. Okay. If our sun encountered a pulsar, will its strong magnetic field compare sun's magnetic field? Okay, there is no way here because sun is really a very minute star. And if another pulsar is there, which is interacting with our sun, definitely our sun will be consumed in that star. Okay, in no time.
Okay. And one question is regarding the recent image of black hole. So
Okay.
how is that image got, like what is the basic principle of getting black hole image?
Okay, let me give you here an illustration. Say for example, if you are using Mathematica software, then there is a function called, I mean, sound function. So you can in fact hear the function, like y is equal to x square is parabola. But if you go with that sound function, you can in fact hear that how this parabolic function you can hear. Okay, so there is some, I mean, frequency or intensity, or you can say some hertz that you can in fact figure out that this is coming in this way and it reverses the parabolic path. This was a simple idea. In the same way, you can go with sine function and cosine function. You can hear those functions. Okay. So whenever this kind of question, if someone asks to me, I'm directly giving this illustration that you can in fact hear any of the function. In the same way, we basically heard these, I mean, black hole collision and gravitational waves, and we found the effect, the relative effect. Okay, with, I mean, in graphical motion, as well as you can create the function. So here the reverse situation is there. You are hearing something and you are creating a graphical representation. And then artists, they got illustration in 3D and simulated the thing, that how this thing happened and how we are getting. So even if you saw some of the YouTube videos for the detection of first gravitational waves, there was a buzzing sound like zoop. So that sound function basically gave you the idea that how you can illustrate those things in 3D.
Okay. So this is regarding the gravitational wave, the first gravitational wave.
Yeah.
And the question was regarding the first gravitational black hole image.
Yeah,
Like,
I mean, I was saying the same thing. That was the, yeah, that was the answer related to the first gravitational wave. But in the same way, the black hole image could be, I mean, created on the basis of its effect on the surrounding medium. So we found the effect of our wave. Say, see, for example, if you see in space, you will see tons of, I mean, radioactivities, okay? And tons of even some X-rays and gamma ray emissions as well. So when you have observational thing, okay, you can in fact immediately tell that these rays are basically coming in different way. Okay, there might be some curvature here. So basically we found the indirect presence of black hole on the basis of those observations, and that's the reason that we could picturize the actual black hole.
okay. And following the, as you say, how black hole affects the surroundings, there is one question. So basically, dark matter is strongly proven by gravitational lensing effects that it provides. But there is also other theories like MOND, which disregards dark matter. So how can MOND theorists explain this gravitational lensing even without presence of matter? Like, how do they do that?
Okay, I am sorry for this thing again, once again, because it's, I mean, beyond my scope of research area.
Okay. Yeah, I don't see any more questions. And it was a very wonderful talk and experience with you, sir. It was a nice talk. So
My
I
pleasure.
call Sitara if you're here to give the bell to give the vote of thanks.
Hello, sir. Once again, that was a really amazing talk. Very broad and gave us a very holistic overview of all the areas that you're working on as well. I would definitely request you to perhaps conduct one more where you can offer more technical information about certain concepts, especially like I think neutron star physics is a area of interest for a lot of students, and we've actually done a couple of projects on that as well. So
Sure.
we would love to have you again. So thank you so much for your time. If there are any other questions, we can just wait for one more minute. If you guys are on the chat box or on YouTube, you can post the question. Otherwise, we will mail your questions to sir, and we'll make sure we are keeping in touch and getting the answers as well. So I want to thank everyone who's been organizing the Cosmic Tales session, and for Kushal for putting everything together, and Sagar for doing a wonderful job of making sure that the meeting is going on well. So thank you again, sir, and hope to have you again on the platform.
My
My
pleasure.
pleasure.
Thanks
Okay.
a lot for giving me this opportunity.
Yeah, I don't see any more questions for now. We will mail you perhaps a list of questions that the students give out later.
Sure.
Sure.
Okay. Thank you so much.
Thank you.